This talk will be about our paper Approximation in Polylogarithmic Space, which is joint work with my advisor Venkatesh Raman and Saket Saurabh, both professors at the Institute of Mathematical Sciences in Chennai, India. This is me, Arindam Biswas, a doctoral student at the same institute. The general theme here is approximation under space constraints. We consider the following questions. What problems can we approximate when we limit the amount of usable space to a sublinear function of the input size? More specifically, we would like to know what can be approximated when this space bound is polylogarithmic. We devise a number of approximation algorithms for problems that over certain ranges of parameters use polylogarithmic space. The model that we work with is the standard RAM model with two restrictions. The first is that the input is read-only, and the second is that the output is a stream. That is, the algorithm can only write something to the output and not read it back as it executes. This in particular prevents the output from being used as some kind of memory. The objective is to use as little additional memory as possible. This model has been used in the study of problems such as sorting, graph reachability, and graph recognition, where it arises naturally. The kind of algorithms we are interested in have also been studied in the parallel RAM model, the PRAM model, where there are NC algorithms known for some of the problems. There is a translation of NC algorithms to the RAM model, which yields polylogarithmic space sequential algorithms, but these algorithms are not necessarily polynomial time. We will start with the following problems: vertex cover and de-hitting set. In vertex cover, the objective is to compute a smallest set of vertices which is incident with all edges in the input graph. In the de-hitting set problem, an instance consists of a ground set U and a family F of subsets of U, which all have size at most d. And the objective is to compute a smallest set which intersects all sets in the family F. There is a simple two approximation algorithm for vertex cover which computes maximal matching and outputs the vertices spanned by the matching as an approximate solution. This is easy to implement, but it might use space proportional to n log n, which is a lot more than what we are after. The maximal matching problem has been studied in the parallel RAM, PRAM model, and there is an algorithm of Luby from 1986 which runs in O of log squared n parallel time, and using the known RAM translation, we can obtain an O of log squared n space sequential RAM algorithm for maximal matching. And from that, we can to approximate vertex cover. Our first attempt at this is to use what's called the bus kernelization rule. Roughly speaking, what the rule does is for an integer k, it retains at most k plus 1 edges per vertex in the graph, and it discards vertices that become isolated as a result. The graph produced has O of k squared vertices, and it has the following property, which is that any minimal vertex cover for G of size at most k is also a minimal vertex cover for G prime of size at most k. And this means in particular that the entire vertex set of G prime is a vertex cover for G. Recall that G prime has at most has O of k squared vertices. We use this fact to obtain an approximation. We use the rule by applying it recursively for values of k from 1 to n. The rule actually also determines if the input graph has a vertex cover of if the input graph does not have a vertex cover of size k. If this is the case, the rule directly indicates that the input graph for a certain value of k, the input graph has no vertex cover of size k. If not, the rule produces the equivalent graph G prime. So in the second case, we get something a non-trivial equivalent graph, and this is the case where we stop the iteration. So for smaller values of k, the rule says that the input graph has no vertex cover of size k, and at some point the rule produces an equivalent graph G prime. At this point, we know that the optimum is at least k minus 1, since the rule had said that G does not have vertex covers of size k for smaller values of k, and it is O of k squared because the entire vertex set of G prime is also a vertex cover for G. So what we do is output the entire vertex set as the solution, and because of this relation, we have an approximation factor of O of square root n. The procedure can be generalized to obtain better approximation ratios at the cost of space. What we show is that for any integer k and any n vertex graph G, one can either determine that G has no vertex cover of size k, or compute a vertex cover for it of size O of 1 by epsilon times k to the 1 plus epsilon. And this can all be done in time n to the O of 1 by epsilon, and in space O of 1 by epsilon times log n. The solution that is produced is obtained from a kernel, but the solution itself is not necessarily a kernel. From this, we have the following result. For any n vertex graph G, one can compute an O of 1 by epsilon times n to the epsilon approximate minimum vertex cover in time n to the O of 1 by epsilon using O of 1 by epsilon times log n bits of. The result can be generalized to de-Hitting set as well. We devise an algorithm that takes as input a universe U of size n and a family F of subsets of U of size at most d, and it computes an O of d by epsilon times n to the epsilon approximate minimum hitting set for this family. The overall running time is n to the O of d squared plus d by epsilon, and the amount of space used is O of d squared plus d by epsilon times log n. The The result can be used to obtain similar approximations for what are called graph deletion problems, as we will see in the following corollary. Consider a class pi of graphs characterized by a finite set of forbidden induced subgraphs. For such a class pi, deletion to pi is a problem where the objective is to delete the smallest possible subset of the vertex set such that the resulting graph is in the class pi. That is the problem, and using this theorem, we show that this problem can be approximated to within O of 1 by epsilon times n to the epsilon in time n to the O of 1 by epsilon using O of 1 by epsilon log n bits of space. The d term in the expressions here disappears in this corollary because for a fixed class pi, the problem deletion to pi can be characterized as can be formulated as a deheating set where d is fixed, and that is why the expressions here all have 1 instead of d. Now we look at a restricted variant of vertex cover where the inputs have maximum degrees bounded by delta. For this variant, we show that one can compute two approximate solutions in time n to the O of delta using O of delta log n bits of space. To do this, we process the input graph in layers. Every layer has a simple structure which we can exploit to compute exact minimum vertex covers for the layers. The layers are essentially forests. Each connected component of a layer can be made into a tree by deleting at most one edge. A layer looks something like this. There is a cycle in it, and removing one edge from the cycle converts the entire connected component into a tree. This is what we exploit to compute a minimum vertex cover for the entire layer. The algorithm starts with the graph of first neighbors of every vertex. So for every vertex, the algorithm only retains the edge to the first neighbor, and this gives a graph G1. This is the first layer. G1 is the first layer, and this layer has simple structure like in the diagram we looked at earlier. Every layer has connected components that can be made into trees by removing at most one edge. For this layer, it computes a minimum vertex cover S1, and then what it does is removes these vertices S1 from consideration. To get the next layer, the algorithm retains only the second edge out from every vertex. So the second layer is the graph of second neighbors minus the vertex cover computed for the first layer. So this is how the second layer is obtained. And for this layer as well, the algorithm computes a minimum vertex cover. and it does this iteratively for layer numbers up to delta. So for every layer from 1 to delta, it does the same thing: compute a minimum vertex cover, remove it, and then compute a minimum vertex cover for the next layer. In the iteration, the layers are all disjoint. The ith layer is a subgraph of the graph of ith neighbors, and it looks something like this. Every vertex retains only the edge to its ith neighbor, and all vertices appearing in vertex covers computed previously, they are removed. So the layers are all disjoint, and because of this, if we compute maximal matchings for all layers and combine them, we have a matching which is also maximal for the entire graph. So maximal matchings for individual layers can be combined to obtain a maximal matching for the entire graph. And because of this, we can say that the minimum vertex covers for individual layers can also be combined to obtain a vertex cover for the entire graph, which is actually a 2 approximation for the minimum vertex cover. So what the algorithm does eventually is output all the vertex covers computed as the solution. It is a 2 approximation because of this argument. The layers are disjoint, and maximal matchings can be combined to obtain a big maximal matching. And the algorithm operates in delta stages. Every stage can be implemented to use O of log n bits of space. So the total amount of space used is O of delta log n. In the paper, we also devise approximation algorithms for restricted variants of dominating set and independent set, which are well-studied problems. In dominating set, the objective is to compute a vertex set of minimum size which is adjacent to all vertices outside it. And in independent set, the objective is to compute a vertex set of maximum size which such that no two vertices in the set have an edge between them. For dominating set restricted to D-degenerate graphs, we show that there is an O of D squared approximation which can be computed using O of log squared n bits of space, and which runs in time n to the O of log n. And for independent set restricted to graphs with average degree D, we show that there is a 2D approximation which runs in polynomial time and uses O of log n bits of space. Now for some open questions. We showed that vertex cover in the general case can be O of 1 by epsilon times n to the epsilon approximated using 1 by epsilon times log n bits of space. What we would like is to be able to 2 or even O of log n approximate vertex cover in the general case using space O of log n. The other open question is about a dominating set, and what we would like to do is devise an O of log n approximation algorithm which uses something close to O of log n bits of space. I would like to conclude by thanking you for your attention, and if you have any questions, please write to me at this address.